All right, we are now going to do our last tests, learn about two new tests to determine the convergence or divergence of a series, and the ratio and the root test. And these are two of my favorite tests, and they're quite fun to use. Again, think back what we've been doing. It's in general the question of determining whether an arbitrary series converges or diverges can be quite difficult. And basically these various tests we've been using are sort of showing different techniques that can be used in certain situations. And at the end of this lecture I'll summarize all those for us. So let's take a look though at the ratio test. So for a ratio test we're looking at series where there's non-zero terms. Okay, so last lecture we introduced the possibility of having some of the terms be negative, some to be positive, and that can be the case here. Now we actually can have some non-zero terms, but for some value of n, n is going from 1 to infinity or whatever, some value of n on, from 100 on or 2,000 on or 3,000 on, the terms in the sequence must all be non-zero. And the reason is we're going to be looking at the ratio of successive terms in this series, and that we're adding up in the series. And obviously if we're dividing by 0, that's problematic. So we're going to eventually have some non-zero terms in these series, hopefully, in order to use this test. So if that's the case, then this series converges absolutely. So notice this is a test for absolute convergence, and we talked about that in the last video. You want to review that and keep in mind if a series is absolutely convergent, then that series is convergent. So this series converges absolutely if what? The limit as n goes to infinity of a n plus 1 divided by a sub n. So this is basically the nth plus 1 term divided by the nth or previous term. So the ratio of the next term in the series of terms that we're adding up divided by the previous term in that series. That ratio, take the limit and notice the absolute value bars, right, of that, which has something to do with why we're saying this will tell us about absolute convergence. If the limit of that ratio approaches a real number that is less than 1, then the series converges absolutely. If that limit approaches a real number that's greater than 1 or is approaching infinity, then the series diverges. So this is a pretty powerful test. Not only, the last test we looked at, the alternating series test, sometimes called the Liveness test, that alternating series test only showed whether or not we converged. But this actually gives us two conditions, right? One condition for absolute convergence and the other for divergence. Now, of course, for less than 1, greater than 1, what's that leave us? 1, right? What if the limit of this is 1? Well, this ratio test is inconclusive. There are examples of series where this limit is 1 and the series diverge. There's examples where the series is converging absolutely. And so we would have to do some other test in this case. All right, so let's make use of this ratio test. I forgot I want to sort of explain why this is the case. And what I want you to think of is I want you to think of the geometric series. If this was a geometric series, what would be true? This ratio is fixed, right? For geometric series, the nth plus 1 term would be found by multiplying the a sub n term by r. So if it was geometric, let's just keep in mind, then a sub n plus 1 is just r times a sub n, and that ratio, right, a sub n plus 1 over a sub n, if I look at the absolute value of that ratio, it's just going to go to what? R a sub n over a sub n, which is just what? Absolute value of r, right? And so what do we say about geometric series? They're convergent if the absolute value of r was what? Less than 1, right? And that's where this is coming into play. So that value of r being less than 1 there's an analogy here. Now, the series that we're looking at, though, are not going to be geometric. I mean, we can use this to prove geometric series are convergent, but we already knew that, right, for geometric series. So really, these are for non-geometric series. But what we're saying is, far out, as long as the terms in the sequence are getting close to a geometric series. In other words, this ratio is approaching some value of r such that r is less than 1 absolute value, then the series looks very much kind of like a geometric series, and because of this behavior that we proved with the geometric series, we can then show that these series will converge. But that's only if this limit, again, is going to be less than 1. Now, the geometric series, remember, was divergent if the absolute value of r was, what, greater than or equal to 1. But here now, greater than 1, of course, we're taking the absolute value, so it's going to be greater than 1 if what, it would indicate that the series diverges. But if it's equal to 1, notice that the test is inconclusive. So that's sort of the borderline issue, which for geometric, we do know if r in absolute value is greater than or equal to 1, greater than or equal to 1, then the series diverges. Okay, so let's make use of this. So one thing you're going to see is, if you're looking at a series and there's a factorial in it, okay, 99% of the time, you're going to want to use the ratio test. The ratio test works very nicely with factorial notation. Okay, so here we're going, right, this is my a sub n, and notice for values of n equals 0 to infinity, the a sub n's are always going to be non-zero. It's important. So let's take a look at the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Now, the way I usually like to write this, by the way, I'll do this one time, is a sub n plus 1 times, if I'm dividing by a sub n, that's the same as the reciprocal, right, multiplying by the reciprocal, rather, of a sub n. So that's what I'm going to do here. And so when I look at this particular one, I get 2, a sub n plus 1. What's that? Just replace n with n plus 1. So a sub n plus 1 is 2 to the n plus 1 over what? Now be careful here. N plus 1 factorial. Was this the way I would write it? That would be incorrect. This might be interpreted as n plus 1 factorial. It's n plus 1, the whole thing, factorial. In other words, you've got to figure out what n is first, add 1 to it, and then take that factorial. Times what? A sub n is just 2 to the n over n factorial, but it's the reciprocal 1 over, so this becomes n factorial over 2 to the n. Okay. Now, first of all, just make this note. Everything in here is non-negative for any value of n, as n goes from 1 to infinity, right? These factorials and 2 to any power that's 0 or more, 2 to any power, period, is going to be positive. And so these are always positive. I've got the absolute value bars. It doesn't matter, right? I can just drop them, and that's what I'm going to do. Now, to simplify this, I want you to realize that 2 to the n is the same as 2 to the n times 2, right? What do I do with these exponents when I'm multiplying? I add them, n plus 1, right? That's what that is, right? And down here, I want you to think about n plus 1 factorial. Remember how factorials work. This is a quick refresher, right? Remember how factorials work, right? If I have, like, say, 4 factorials, 4 times 3 times 2 times 1, 3 factorials, 3 times 2 times 1, 5 factorials, 5 times 4 times 3 times 2 times 1, and so on. We got, all these. But the key is to note in these relationships that, for instance, 5 factorial is what? 5 times 4 times 3 times 2 times 1. That's 4 factorial. Okay? And similarly, we could say 6 factorial would be 6 times 5 factorial, and so on. And so the idea is, if I wanted to look at what is n plus 1 factorial, okay, n plus 1 factorial, that's going to be what? 6 factorial, it's 6 times 5 factorial. N plus 1, it's n plus 1 times what? 1 less than, right? N plus 1 would be what? N factorial. So that's a very key relationship that we would like to use in this analysis. So I'm just going to rewrite this as n plus 1 times n factorial, right? Times n factorial over 2 to the n. And I've got rid of the absolute value bars because everything's positive. But do you see what happens then? Of course, 2 to the n divided by 2 to the n, those cancel out. And here's the beauty, right? N factorial divided by n factorial, that's all gone. And that's a big mess, right? N factorial is n times n minus 1 times n minus 2 all the way down to times 3 times 2 times 1. So that's a big mess to get rid of. And look, everything clears up very nicely. What am I left with? Up top, 1 times 2 times 1 is 2. In the bottom, n plus 1 times 1 times 1 is just n plus 1. So all this simplifies down to just this, and what's happening to this expression as n goes to infinity? Well, it's clearly going to 0, right? Denominator is going to infinity. 2 divided by a larger and larger quantity is going to 0. And what do we know about this limit? Well, it is less than 1. And that's important because if this limit is less than 1, then the series what? Converges absolutely. So our series converges absolutely. And of course, remember that means the series itself converges, right? So that was that theorem we looked at in the last video. But there we have it. The series converges using ratio test. Okay. Let's look at another one. This one's got a little sign changer. Remember we talked about sign changers in the last video, -1 to the n. So we want to take a look at this. That's the a sub n. So I'm going to look at the limit as n goes to infinity of a sub n plus 1 over a sub n. So remember how I look at that? A sub n plus 1. What's that? Replace n with n plus 1. Slide this down here a little bit. Okay, so replace n with n plus 1. So I have -1, 2, the n plus 1. And n, be careful, becomes n plus 1 quantity squared there. And 2 to the n plus 1. And then divide by a sub n is the same as what? Multiplying by the reciprocal of a sub n. This is a sub n, so the reciprocal of that will be 2 to the n over -1 to the n squared. Now we got absolute value bars. What's the net effect of the absolute value bars? The net effect of the absolute value bars is -1 to the n plus 1, right? I'm going to take the absolute value of that. Same thing down here. I mean, don't worry about canceling. We could cancel and say there's a -1 left up top here, but when you take the absolute value of -1, it's going to be +1. Okay? So here, though, remember, this is the same as 2 to the n times 2, so that 2 to the n and that 2 to the n will cancel. And so what am I left with? Since I've got rid of my sign changers essentially with the absolute value bars, I can get rid of the absolute value bars. And I just have to limit, as n goes to infinity up top, I just have n plus 1 squared. And in the bottom I got 2 times n squared. So what's this? Notice the limit of this expression is infinity over infinity. It's indeterminate. Okay? So I can use L'Hopital's rule if I wanted to. Actually a couple times, but let's just notice if I expand this out, I get n squared plus 2n plus 1 all over 2n squared. And most of you already know what this limit's going to be because the degree of the top and bottom are the same, both n squared, right? Then the highest degree term up top is going to dominate as n gets bigger and bigger. As n goes to infinity, this thing is approaching n squared divided by 2n squared. And n squared divided by 2n squared is 1/2. So you can get that also by L'Hopital's rule. You have to use it twice. You get infinity over infinity after the first time, and you do it again, and then you'll get this to 1/2. Okay. So what's that mean, though? This is less than 1. And so again, the series converges absolutely. Absolutely by the ratio test. So that's real important because, notice this series has an alternating series, but it's absolutely convergent, meaning the series itself is also convergent. Okay, so that's the ratio test. And it's real nice. It just kind of feels good to cancel stuff out and simplify this. Okay. So there's lots of varieties of this, but obviously when you see factorial notation, that's a good hint that ratio test is going to be used. Let's look at this one, which has a factorial. Now, listen, interesting enough, it's got, notice in parentheses 2n. So that means you have to figure out 2 times n first, right? Double n, and then you take the factorial. That's what that means. So notice that 2n factorial is not equal to 2n factorial. This is multiply 2 by n, then take the factorial. This is take n factorial and then multiply by 2. All right, so let's look at this limit as n goes to infinity. And we're looking at this ratio again, using the ratio test. A sub n, this is the a sub n's that we're adding up here. And so limit as n goes to infinity. A sub n plus 1. Now we're careful. If I replace, so I got 2n factorial. If I replace n with n plus 1, excuse me, I've got 2n. If I replace n with n plus 1, notice what I get there. In parentheses, right, I'm replacing n with 2n. And this is really what? 2n plus what? 2, right? Distributing that 2 through. And so that's important here because I'm going to get 2n plus 2 factorial over 10 to the n is replaced with n plus 1. Divided by a sub n is multiplied by the reciprocal of this, and the reciprocal of this is 10 to the n over 2n factorial. Okay. So again, absolute value bars, in this case there's no negative numbers at all in this. They're all positive quantities for n equal 1 or more, and so this you can just get rid of the absolute value bars, and we will in a minute. Notice here, if I simplify, dividing top and bottom by 10 to the n, right, then this just leaves me 10, doesn't it? Because 10 to the n plus 1 is 10 to the n times 10. But let's see what we have up top here. Get rid of the absolute value bars. Up top, I've got 2n plus 2 factorial. How does that cancel? Well, be careful. The first term in 2n plus 2 factorial is 2n plus 2. Okay? What's the next term? Remember, we multiply, if I have 8 factorial, it's what? 8 times 7 times 6. So it's the whatever n factorial, n times what? All the integers less than or equal to n. Or n times all the integers less than it. So what's the next lowest integer from 2n plus 2? Just subtract 1 from 2n plus 2. It gives me what? 2n plus 1. Right? And then subtract 1 again. It's going to be 2n. And then 2n minus 1, and 2n minus 2, and so on. But from 2n minus 1, 2n minus 2, and so on, that's just 2n factorial. Do you see that? And I stopped there because on the bottom I got what? 10 times 2n factorial. And so now do you see that these right here are going to cancel? Okay. And so what do I have? The limit as n goes to infinity. Let me just FOIL that out. I get 4n squared. I get 2n plus 4n is 6n. 2 times 1 is 2. If I FOIL that out, all over 10. Really, I didn't need to FOIL it out, but think about what's happening here. The bottom stays at 10. What's the top going to? Infinity, right? The form of this limit is infinity over 10. That is not indeterminate. That is clearly going to infinity, right? And if this limit is infinite, then the series diverges by the ratio test. Okay. If the limit comes out to be any real number greater than 1, the series will also diverge by the ratio test. Now, we did say in certain cases this limit could come to be 1, and what happens then? Well, it's inconclusive. And I just want to show you why, or show you an example of why that's the case. It's inconclusive. We know what these series do. Right, this is the harmonic series, right? What do we know about this? This is divergent, right? It's a harmonic series, or it's a p-series with p equal to 1. This one, on the other hand, is what? Convergent. It's a convergent p-series. Right, p equal 2, which is greater than 1. If p is greater than 1, p-series is convergent. So I just want to use the ratio test in both of these. And if you look at this one here, I'll take the limit as n goes to infinity. A sub n plus 1 is 1 over n plus 1, right? Just replace n with n plus 1. Times the reciprocal of a sub n is n over 1, right? Absolute value bars I can take out because n is going to infinity. It's just n over n plus 1. And I think you can see with one step of L'Hopital's rule that limit's going to be 1, right? Because it's infinity over infinity, but the ratio, if we use L'Hopital's rule, I get limit n goes to infinity 1 over 1, which is 1. Okay. At the same time, if I take a look at this one, limit n to infinity, absolute value of what? 1 over n plus 1 quantity squared, that's a sub n plus 1, times the reciprocal of a sub n is n squared over 1. Again, I can get rid of the absolute value bars. Up top I got n squared. Down below, if I follow this out, I've got n squared plus 2n plus 1. But again, that ratio we've seen already, that's going to 1. And you see why it's inconclusive? Because we have examples of divergent series where that limit is 1, and examples where a convergent series where the limit is equal to 1. So in general, if the limit is 1, we're going to have to do something else. We're not going to be able to use the ratio test. Now, related in some way to the ratio test, or very similar, is something called the root test. I want to show you this very quickly. If we have a series, then the series is going to converge absolutely if the limit as n goes to infinity of the nth root of the absolute value of a sub n is less than 1. Okay? And diverges if that same limit is greater than 1 or is infinite. The root test is inconclusive if that limit is equal to 1. So if you compare that, it's very similar in terms of convergence, divergence, and inconclusiveness. Of course, the limit, what we're taking, is not a ratio anymore, but it's a nth root of a sub n. Okay, so I look at the a sub 1. I look at the square root of a sub 2, absolute value, of course, and the cube root of the absolute value of a sub 3. The fourth root of a sub 4, the fifth root of a sub 5, and so on. And I'm looking at that sequence, and I'm trying to see what the limit of that sequence is. Now, if it's less than 1, then this series is absolutely convergent. If that limit is greater than 1, then that series diverges. And it's inconclusive if it's 1. Now, here's an example. So take a look at this. This is going to be a prime candidate for root test because it has an nth power, right? So when n is 1, I got to the first power, n is 2, I got to the second power, n is 3, I got to the third power. And the root test is going to be able to help with this. Okay. So let's see what we get here. I'm going to take the limit as n goes to infinity. Of what? The nth root, make a big nth root here, of the absolute value of just a sub n. There's no a sub n plus 1. A sub n is 3n divided by 4n plus 5, all to the nth power. Okay. Now I've got the absolute value bars in here, but if you think about it, for this expression, for any value of n that's greater than or equal to 1, right, this is always a positive number. Right, so the absolute value bars we can just get rid of. And when I take the nth root of something to the nth power, what happens? The nth root is the same as what we could think of it, fractional exponent, right? So 3n over 4n plus 5 to the n, and then the nth root is the same as the 1 over n power. But here, what do we do with these exponents? We multiply them, right? N times 1 over n is just 1, right? Some of you already knew that, right? The nth root of something to the nth power cancels, they cancel each other out. They're inverse operations. And we're just left with, what, 3n over 4n plus 5. And I think everyone knows that limit already. Let's just use L'Hopital's rule because it's infinity over infinity. Most of you know exactly what's going to happen, because the degrees of the top and bottom are the same. Derivative of 3n is 3. Derivative of 4n plus 5 is 4. I just get 3/4, so a lot of you already knew that. But the limit 3/4 is what? This limit is less than 1. And therefore, the series converges. Absolutely. By the root test. The root test works very nicely when we have those situations. And this is real helpful in certain cases. Obviously, you see the power of n. Let's take a look at this series. And if you hadn't had the root test, let's just say you don't have a root test. This is weird. 5,000 n and then n to the n. If you didn't have the root test and you were just saying, let's sort of look at this series. Let's do with n equal 1. I get 1 to the first power up top. That's just 1. And I get 5,000 to the first power. That's 5,000, right? And then I do n equal 2. Let's see, I get 2 squared. That's 4. And down at the bottom, I get what? 5,000 squared, right? Which is what? That's 25 million. Okay. And then 3, I get 3 cubed, which is 27. 3 cubed is 27. 5,000 to the third power. 5,000 to the third power is 125 thousands, millions, billions. 125 billion. Okay. As you're doing this, you might be thinking, well, holy moly, 4 divided by 25 million, pretty small. 27 divided by 125 billion, really small. And the next one, you can think about 4 to the fourth power. It's a pretty big number, but 5,000 now to the fourth power. I mean, you're talking hundreds of trillions. It seems like these terms are going rapidly to zero, and it would seem like they're vanishing away, and that this series would have to converge because these terms are getting smaller. But hold on. If you keep going, in fact, if you keep going quite a while, n equal 1, n equal 2, n equal 3, eventually you're going to get to n equal 5,000. By the time you get to the 5,000th term, what is this? What is the 5,000th term? 5,000 to the 5,000 over 5,000 to the 5,000. What is that? 1. These numbers, these were getting very, very, very small, very, very, very tiny. But eventually, somewhere along in the process of going from n equal 1 to 5,000, you kind of rebound. You get to real small numbers. It's like 0.000000 or whatever. Something very small. And these are getting even smaller. And they just start vanishing away. Your calculator might even say they're 0 because of round-off error, or probably using scientific notation. E to the 10 times 10 to the negative 50 or something. I don't know. Real small. But eventually they start coming. When we get close, we come back all the way to 1, which in comparison is a pretty big number. But look at the next one. When n is 5,001, I'll get 5,001 to the 5,001 power over 5,000 to the 5,001 power. Now what's happening? Well, this now, because the base is 1 more than this, the exponent's the same, this is now bigger, all right? We've multiplied 5,001 times itself 5,001 times, 5,000 times itself 5,001 times, right? So this is now going to be more than 1. And if you keep thinking about the process now the top is going to start getting a lot bigger, because what's next? 5,002 to 5,002 power versus 5,000 to 5,002 power, right? That's even bigger, and eventually these get bigger and bigger. So the series actually does diverge. I do all that knowing that we could have just used the root test very simply, and let's do that. The root test says take the limit as n goes to infinity of the nth root of the absolute value. I'm going to go rid of the absolute value. We'll say it down here, because all the values of my a sub n's right from n equal 1 to infinity are positive. So this is the nth root of n to the n over 5,000 to the n. Right. And so that's all to the 1/2 power, right? Really to the 1/2 power. And notice a quotient raised to a power, I can take each one of these and raise them to the 1 over, I said 1/2 power, what did I say? 1 over n power. Nth root is 1 over n power. N, sorry, 1 over n. And all right, then of course this is just what? N over what? 5,000. Now 5,000 is a pretty big number, but if n's going to infinity, what's going to happen? This thing is going to go to infinity, and therefore the series diverges by the root test. Okay, the root test only going to work nicely if you have particular types of series, right, where you're raising to some power involving n or something close to n. It could be 2n power or 2n plus 1 power or something like that, possibly. There might be some times where you can use it. If it's not something like that, then the root test may not be very useful, right? So very specific test, okay, but very nice. So this sort of brings to an end all the different tests we want to look at, and the reason we have spent the time looking at these tests is we need to know really what's happening to infinite series, particularly when we go to power series, and we'll talk about that in the next lecture. But I want to just show you then a summary of all the tests that we've learned so far. And this sheet will be posted with the completed notes for this section, so you can have it, and as a tool as you're doing homework and everything, especially when it says use any test that we've talked about so far. So let's talk about, and really these are kind of in the order you would think to use them. If it says use any test at all, I would start with the nth term test, which is also called the divergence test. And you look at a series, if the terms of the series that you're adding up, right, the sequence of terms that you're adding up, if that sequence doesn't have a limit that's 0, If the limit is not 0, then it's diverging. Doesn't tell us anything whether it's convergent, right? The limit is 0. Remember, that doesn't mean it's convergent. Okay? Doesn't mean the series is convergent. The sequence is convergent, but it doesn't mean the series is convergent. Okay? So that's the first test. If I can show that, I'm done. See, if this is true, series diverges, end of story. Don't even have to think about any other test. You don't need to show multiple tests, right? There may be multiple tests that apply. Okay? But you don't have to use all of them. Just one. Geometric series we talked about right again. And if the ratio in absolute value is less than 1, the series is convergent. If it's greater than equal to 1 in absolute value, then the series is divergent. And for convergent series, we even have a formula for the sum of the series, which is not something we normally have for a lot of series. We just know whether or not they converge or diverge. We talked about P series. Right? Convergent if P is greater than 1, divergent if P is less than or equal to 1. And of course, P series came out of the integral test. Here's the integral test that we talked about for a series where I create a function f of x such that f of n equals a sub n for n equal k to infinity. If the improper integral from k to infinity converges, then the series converges. If that integral diverges, then the series diverges. You do have to have the function f being continuous, positive, and decreasing on that interval. Direct comparison, right? So there we talking about positive term series, right? Greater than 0. If the b sub n's are greater than the a sub n's and b sub n converges, then the a sub n's are going to be convergent. If the a sub n's are greater than the b sub n's and the b sub n diverges, then the a sub n's are convergent. So remember that it's real important that there's only these two possibilities, and the direction of the inequality has to be there. So again, these are the things that you have to show. When we're talking about show support, you have to find this limit to show support for this. You have to find the value of r to show support for this. You have to find the value of p, and that's pretty easy, but to show support here. You have to evaluate these integrals to show support here. You have to show these inequalities, right, exist, and then show that use probably something up here to show b sub n or b sub n converges or diverges series. Limit comparison, same thing. A little more powerful in some ways than direct comparison. You just have positive term series again. Look at the ratio. If the limit is some positive number of the ratio, a sub n to b sub n as n goes to infinity, then both series will either converge, right? This is the criteria. This column right here is the criteria for a sub n converging again, convergence of a sub n. They both converge together or they both diverge together. Alternating series test, sometimes called the Liveness test, right? So we looked at that in the last video. And there's two conditions you have to show here. It only shows conditions for convergence, not divergence. Okay. In fact, though, if the limit of n goes to infinity of a sub n is not equal to 0, obviously you're going back to the nth term test, right, back up here, and being able to say it's divergent. But both of these have to be shown or proved. A lot of times it's simple, but you need to at least state that they're true. And then the ratio test we talked about, right? Conditions for convergence if this limit is less than 1, greater than 1, inconclusive if it's equal to 1, and then for the root test, right? Very similar, we just looked at those. So there it is. There's the complete summary of all your tests. And that's sort of the order I would do if I'm trying to say, which test do I use? Start here and work your way down. Okay. Now, I would say, you might, if you look at it and you see, hey, there's an n factorial in it, you might jump right all the way down to the ratio test. Maybe, you might try that. But it's always a good idea to think about the nth term test, see it diverges. See if it diverges. Remember, if the limit as n goes to infinity of a sub n is equal to 0, that tells us nothing. We would have to do something else. Okay, so that wraps up all our different series tests. I'm real excited. Our next video, then, we will talk about power series, and that will lead into our final topic in the course on Taylor series. So this will also show us a way to bring everything back to integration techniques and the definite integrals, how to find definite integrals. So we'll be talking about that in the next lecture.